Hey folks, welcome to another set of Intro Chem video notes. In today's lesson, we're going to learn about the Bohr model of the atom and atomic emission spectra. More specifically, the unofficial standard that I'm holding you accountable to is to understand the Bohr model of atoms and how it helps illustrate the reason for atomic emission spectra. Let's get started. So now that we understand the basic structure of an atom and how to determine how many protons, neutrons, and electrons there are, we can focus a little more on the electron, the particle that's responsible for all chemical bonding. There have been several models of the atom over the years, but they all have one thing in common: inaccuracy. As with all models in science, the atomic model is just an illustrative representation that serves to help us understand some aspects of an atom at a time. A model can never really be good enough to understand everything there is to know about the thing it's modeling. For instance, one of the more current models of the atom is the electron cloud model. This describes the atom as having a nucleus with a cloud of space around it where electrons may exist. This model falls short of a perfect explanation of an atom because it doesn't actually show the electrons or discuss the electrons' energies. It does do a great job of showing the wave-like properties of electrons, though. The Bohr model of an atom is a bit less current, doesn't represent the wave nature of electrons at all, and does not do a great job of representing the relative size comparison of the nucleus to the rest of the atom. It does, however, do a fantastic job of showing electrons as particles with very specific energies. It also does a really great job of showing how many electrons are available to participate in chemical bonding, which is really what we're concerned with in this class. The Bohr model represents the nucleus as a compact ball in the middle of the atom. Sometimes we even write the number of protons in the nucleus, or the chemical symbol with its mass number, so that we have more information about what's in the nucleus. Around that nucleus are rings called energy levels. These energy levels are where we're going to place our electrons. It's important to remind ourselves that these energy levels are not attempting to represent the electrons as orbiting the nucleus in a circular pattern, or to describe the location of the electrons. They're simply there to try to describe how much energy our electrons have. The first level closest to the nucleus is labeled n equals 1. The second level is n equals 2. Third level is n equals 3, etc., etc. The further away the energy level is from the nucleus, the higher its n number, or principal energy level number. And the further away it is from the nucleus, the more energy that level has. Each energy level can hold a maximum of 2n squared electrons. That equation will come in handy, but we'll talk about that a little bit more on the next slide. The highest occupied energy level, in other words, the ring that is the furthest from the nucleus and has electrons in it, is called the valence shell. The electrons in the valence shell are called valence electrons. Valence comes from the Latin word valere, which means to be strong. So valence electrons are the strongest or most energetic electrons, the ones furthest from the nucleus. This is important information because knowing how many valence electrons an atom has and in what level those valence electrons are can tell us a lot about how that atom will bond with other atoms or what row in the periodic table that element's in. So here's how you use this information. The first step is to know how many electrons you're dealing with. We've already learned this, but here's a recap. If it's an atom, it has the same number of electrons as it does protons. If it's an ion, the charge of the ion is equal to the number of protons minus the number of electrons. Essentially, just take the number of protons minus the charge, and that will get you the number of electrons. Once you know how many electrons you need to place, start by placing them in the first energy level. Fill up that energy level until you hit its maximum, then move to the next level. As we said earlier, each level can hold up to 2n squared electrons. That means in the first energy level, there can be a maximum of 2 times 1 squared, or just 2 electrons. In the second energy level, you can have 2 times 2 squared, which is 8 electrons. The third can hold 2 times 3 squared, which is 18 electrons, and so on and so forth. There's only one other trick to doing this. You cannot have more than 8 electrons in the valence shell of an atom. So if you're filling level 3 or higher, the ones that can hold more than 8 electrons, you have to stop at 8. Add 1 electron to the next level up, and then go back down and finish filling that level. For example, let's say we want to draw a Bohr model of a bromine atom. Bromine has atomic number 35, which means as an atom it has both 35 protons and 35 electrons. Since the n equals 1 energy level can only hold 2 electrons, I'm going to place 2 electrons in it. And now I have 33 left to place. The n equals 2 level can hold 8 electrons, so the next 8 will go there. This gives me 25 left to place. The n equals 3 level can hold 18 electrons, but I'm only going to place 8 in it at first, leaving me with 17 left. Since I can only have 8 electrons in my valence shell, and n equals 3 is my valence shell currently, I cannot put any more electrons in that level yet. What I can do is go ahead and place 1 up in the n equals 4 level. This gives me 16 electrons left to place, and now I can go back down to the n equals 3 level and fill it the rest of the way. I can place 10 more electrons in level 3 for a maximum total of 18, and that gives me just 6 electrons left to place. The 4th level currently has 1 electron, so I can add my remaining 6 there for a total of 7 in the 4th level. That 4th level is my valence shell, and I have 7 electrons in it, so that tells me that a bromine atom has 7 valence electrons. We fill from the first energy level and work our way up because electrons like to be at the lowest possible energy levels they can be in. When the electrons are arranged like that, we call it the ground state of an atom. If we excite the atom with the energy from heat or electricity, some of that energy can get absorbed by an electron, and when this happens, the electron gains energy and jumps up to a higher energy level, and now the atom's in what we call an excited state. When it falls back down, it has to release that energy again. Electrons release energy in the form of photons, or light particles. The energy of the photons is determined by how much energy the electron has to release. Different photons with different energies will have different properties. For example, a higher energy form of light is X-rays, or ultraviolet rays, while a lower energy form of light would be radio waves, or infrared. The more energetic light can cause damage. I always remember this because ultraviolet light can burn your skin, like a sunburn, while infrared is the stuff we use to make remote controls on our TVs. You can point a remote at your skin all day long and you're not going to get burned by it. So why do we care about the light that gets released by electrons? That's a great question, which can be answered by thinking more about the structure of an atom. Every element has a unique number of protons, right? Protons, being positive, attract electrons since they are negative. So the more protons you have in an atom's nucleus, the greater the attraction the electrons feel, and the closer they'll be pulled in towards the nucleus. Changes in distances from the electron energy levels to the nucleus causes changes in the energies associated with those energy levels. Again, the closer it is to the nucleus, the less energy it has, right? Essentially, what this all boils down to is that every element has its own unique set of energy levels, and as such, has its own unique set of light that can be released from its electrons falling down in energy levels. This series of bands of light produced by an atom is called its atomic emission spectrum. Every element has its own unique atomic emission spectrum, so we can use that to identify what elements might be present in something. Here are some examples of the atomic emission spectrum of different elements. Notice that no two of these are exactly the same. So how is this useful? Well, if you like fireworks, or so-called neon lights, this phenomenon is for you. The excitation of electrons, then falling back down to their ground state in the atomic emission spectra they produce, is what's responsible for the several different colors of fireworks and neon lights that we can make. This is also an important phenomenon because we can analyze the electromagnetic spectrum of light given off by faraway objects like stars to determine what atomic emission spectra, and therefore what elements, might be present in that object. Another fun fact, which we'll try to go over in class, is how light mixes together. The sun is considered white light. If you look at it through a prism or diffraction grating, you see a full rainbow. If you look at the light given off by a particular element, you only see that element's atomic emission spectrum, not the whole rainbow. The colors of light from the atomic emission spectrum combine to form the colors we see. For example, actual neon lights are a bright reddish orange, which, when separated out, is largely a combination of different wavelengths of red, orange, and yellow lights, with an obvious emphasis on red. Color mixing with light is very different from color mixing with paint. Instead of red, blue, and yellow, the primary colors of light are red, green, and blue. Interestingly enough, the three major secondary colors happen to be the same as the colors of ink for printers: yellow, cyan, and magenta. Well, that's all for today, folks. The big thing I want you to take away from this lesson is the Bohr model of the atom, how to draw it, and how to use it to determine the number of valence electrons an atom or ion has. It's also nice if you know and understand the concepts behind atomic emission spectra, but we're not going to dig too deep into it or do the math behind it this year. As always, if you have any questions, ask.